Welcome to lecture 10 on stochastic processes. First, we recall that in lecture 9, we have seen about first entrance theorem, which actually relates the probabilities Pij to Fij's by this equation. Okay, that means Pij n is equals to summation r from 0 to n Fij r Pjj n minus r for all n greater than or equal to 1. And in the same lecture, we have also seen the upper and lower bounds for Fij, where Fij is the sum from n from 1 to infinity Fij n. That means it is the probability that is starting with state I, the system will ever reach state j. So, we have seen the upper and lower bounds for this probability. Now, we proceed for some more theorems related to recurrent and transient states. So, for that we first define some generating functions. So, generating functions. Actually, these functions will be required to prove next theorems. So, let Pii s is equals to summation n from 0 to infinity Pii n s to the power n. That means it is generating function of transition probabilities Pii's. Now we know that Pii 0 is actually 1. So it will be 1 plus summation n from 1 to infinity Pii n s to the power n. Of course, we take s mod s less than 1 for the convergence of this generating function. So, let Pii is this and Fiis is equals to summation n from 0 to infinity Fii n s to the power n. That means it is generating function of first transition probability Fii n. So, again we know that Fii 0 is actually 0. So, this can be written as summation n from 1 to infinity Fii n s to the power n mod s less than 1. So, let these two functions be the generating functions of the sequences Pii n and Fii n respectively. Okay. So, first we will see what is the relationship between Piis and Fiis. That means we will focus upon the relationship between these two generating functions. So, recall from the first entrance theorem. So, from first entrance theorem, we have Pii n is equals to summation r from 0 to n Fii r Pii n minus r, which again we can write because Fii 0 is 0. So, we can write it down r is equals to 1 to infinity Fii r and pii n minus r, and this is true for all n greater than or equal to 1. So this implies that PIIN, if we multiply on both the sides by s to the power n, then we will have this is equals to r from 1 to infinity FIIR PII n minus r multiplied by s to the power n. And this is again, this is also true for all n greater than or equal to 1. So since this is true for all n, we can take the sum n from 1 to infinity on both the sides. So this will be PIIN s to the power n is equals to summation n from 1 to infinity summation r from 1 to no, this was not infinity, this is n, so r from 1 to n FIIR and PII n minus r and s to the power n. So now we can see that we will interchange these limits. So see what are the limits. R varies from 1 to n, r varies from 1 to n varies from 1 to infinity. So if we interchange these limits, what we will get, summation n from 1 to infinity PIIN s to the power n, and when you interchange the limits, then r will range from 1 to infinity and n will range from r to infinity. So this is FIIR, this PII n minus r, and this s to the power n can also be written as s to the power r multiplied by s to the power n minus r. Okay. So if you separate these two things, r from 1 to infinity FIIR and s to the power r, and summation n from r to infinity PII n minus r s to the power n minus r. Now you can see that this can be written as this. If we take n minus r, if we put n minus r as PII for some k, okay, so this will be s to the power k. So if n starts from r and k is nothing but n minus r, so k will start from 0 and it will be 0 to infinity. Now what we have, this is n from 1 to infinity PIIN s to the power n, which is, if you see here, PIIS is equals to 1 plus summation n from 1 to infinity PIIN s to the power n. So this quantity will be PIIS minus 1. So this is PIIIS minus 1. And what is this? R from 1 to infinity FIIR s to the power r. This is nothing but FIIS. And what is this? This is PIIS. So from here we can write out PIIS minus FIIS PIIS is equals to 1. So it will give us PIIS multiplied by 1 minus FIIS is equals to 1, which ultimately gives us PIIS is equals to 1 divided by 1 minus Fii S. So this is the relationship which we are getting here between the generating functions Pii and Fiis. So we will use this relationship. So clearly the range for S is mod S less than 1. So we will use this relationship to prove some results. So before writing down the main theorem, we will also require one famous lemma, which is Abel's lemma. So ABELS, Abel's lemma. So this lemma will also be required to prove the next result. So what it says that if summation n from 0 to infinity an converges, that means if this series converges, then limit s goes to 1 minus, that means left hand limit, summation n from 0 to infinity an s to the power n, that means the generating function of sequence an. So this lemma says that if this series converges, then this generating function will be same as this series, the value of this series. So if I call it A, for example. So second part says, so this says that if this series converges, then this limit will be equal to the sum of that series. And if elements of these series are non-negative, and this limit s goes to 1 minus summation n from 0 to infinity an s to the power n, if this is A and this is either finite or infinite, then this summation n from 0 to infinity an is A. So this says that if this converges, then this value will be same as this value of the series, and it says that if this converges or diverges, then the values will be same. So we will not provide the proof of this lemma, we will not see that, but we will use this lemma to prove the next result. And what is the next result? The next result actually provides us the practical method to check for the recurrence or transient states. So what next theorem says? First we see the statement of the theorem. So this theorem says that I state I is recurrent if and only if summation n from 0 to infinity Pii is infinite. So we have seen that what was the recurrent state? I is said to be recurrent if summation Fii n from 1 to infinity is equals to 1. So that was the definition. Now we are saying that if the n step transition probabilities, if you know those probabilities and you add them and this series diverges, then I will be recurrent. And this condition is if and only if. So we will prove both parts here. So for to prove this theorem, we will require this relationship between capital PII and capital FII and this Abel's lemma. So what is the proof? How it goes? So now, so we have to prove first that if state I is recurrent, then this summation will be infinity, and then we will show that if this summation is infinity, then I will be recurrent. So first, assume that state I is recurrent. And what does that mean? So which means summation FIIN, n ranges from 1 to infinity, this summation is 1, because this is by definition. So or equivalently you can say that summation FIIN, n ranges from 0 to infinity is 1, because we know that FII 0 is 0. So now we use the part 1 of Abel's lemma. And what it says? It says that, so what is the part 1 of Abel's lemma? It says that if this series converges, so you just replace AN by FIIN. So you can see that this series is equals to 1. That means this is a convergent series. So it satisfies the assumption of part 1. So if this series converges, then this limit will be this. So by part 1 of Abel's lemma, what we will have, you just replace AN by FIIN. So what we will have? We will have limit s goes to 1 minus summation n from 0 to infinity. AN will be replaced by FIIN s to the power n. And by this lemma, this must be equal to summation n from 0 to infinity FIIN, and which is given to us is 1, which is 1 for us. So what it implies, see, what is this? Summation n from 0 to infinity FIIN s to the power n. This is nothing but FIIS. So it says that limit s tending to 1 minus is 1. Okay. So what we have shown till now, that generating function, if you take the left hand limit going towards 1, then it will be 1. Now we will use that identity which we have just shown. From the identity, which identity? PIIS is equals to 1 upon 1 minus FIIS. From this identity, it follows that if you take the limit s tending to 1 minus PIIS, then this will be nothing but limit s tending to 1 minus 1 upon 1 minus FIIS. Now you have seen that limit of FIIS when limit s tending to 1 minus is 1. So if it goes 1, then this will be 1 upon 1 minus 1. That means 1 upon 0. So this limit will be plus infinity. So now this limit is plus infinity, means this is nothing but, what is PIIS? PIIS is PIIN s to the power n. n from 0 to infinity. So what you are saying? You are saying that limit s tending to 1 minus this is infinity. Okay. Now again, if this limit is infinity, now we use part 2 of Abel's lemma. And what it says? It says that if an's are non-negative, so you just replace an by piin. Now see, your piins are non-negative. Okay. And limit s tending to 1 minus summation n from 0 to infinity an s to the power n is something which is finite or infinite. So if you replace an by piin, then this is infinity. Then this result says that this summation should be a, which is infinite. So from part 2 of the Abel's lemma, since this limit is infinite, so by this limit s tending to 1 minus pii, and this is oh sorry, this was already written. Something is, this is very slow actually. So what it says, limit s tending to 1 minus this was infinity. Okay. So by part 2 of Abel's lemma. So by part 2 of Abel's lemma, what we have? We have summation, this was our an, so summation piin, n ranges from 0 to infinity, this comes out to be infinity. So we have completed the first part, that if I is recurrent, then this sum is infinity. So we are using Abel's lemma here again and again to show the results. Now we go backward and again we will use the Abel's lemma. What it says, now we want to show that if this sum is infinity, then the result that state I is recurrent. So we will show that using contradiction. So now assume that summation piin n ranges from 0 to infinity diverges. That means it is infinity. Now we have to show that state I is, so what is our claim? Our claim is state I is recurrent. This we want to show. So we will show it by contradiction. So assume, if possible, that state I is not recurrent. That means state I is transient. Okay. So if state I is transient, what does it mean? It means that summation fiin n ranges from 1 to infinity is finite, is less than 1, or equivalently fiin n ranges from 0 to infinity is less than 1. So that means this series converges. So again we will use part 1. So applying part 1 of Abel's lemma. What that says? If series converges, then limit of generating function at 1 will also be convergent. So it says that limit s tending to 1 minus, and what is the generating function? Generating function will be n from 0 to infinity f I n s to the power n. So it says that this limit will be same as this sum, n from 0 to infinity f I n, and this sum is less than 1. So what ultimately we have? We have that this clearly implies that limit s tending to 1 minus of f I s is less than 1, because this sum is nothing but FIIS. So now limit s tending to 1 minus FIIS is 1. So this again implies that limit s tending to 1 minus PIIS, because we know that PIIS is nothing but 1 upon 1 minus FIIS. So since this limit of FIIS is less than 1, this 1 minus FIIS will be positive number. So this will not diverge. This will be a finite number. Okay. So since this is a finite number, again we will use the Abel's part 2 of the Abel's lemma, because now here generating function is finite. This limit of generating function is finite, and we can write it down in terms of series n from 0 to infinity PIIN s to the power n is finite. So what you are saying? What is PIIS? PIIS is nothing but summation n from 0 to infinity PIIN s to the power n. So what you are saying? You are saying that this limit is finite. So again, by using second part of the Abel's lemma, this series PIIN n ranges from 0 to infinity s to the power n should also be finite. How? Using part 2 of Abel's lemma. So you can see that we are again and again using part 1 and part 2 of Abel's lemma. So what you are getting? You are getting that not s to the power n, only series. This series is finite. So what you are getting? You are getting a contradiction, because your assumption was this. If you see your assumption, you have already assumed that summation n from 0 to infinity PIN is infinity. You have assumed this one, and what you are getting? You are getting that this summation is finite. So this clearly contradicts your assumption. So which contradicts the original assumption. The original assumption. What was your original assumption? Original assumption was this, that this sum is infinite. So hence we can say that, thus we can say that state I is actually recurrent. So we have shown that if this series diverges, then a state is recurrent, and if state is recurrent, then this series will diverge. So what about the case when I is not recurrent? That means I is transient. So that is a straightforward corollary of this theorem. So it clearly says that I state I is transient if and only if this PIIN n ranges from 0 to infinity, if this is finite. How? Because if I is transient and this is infinite, then I must be recurrent, which is not the case. And if this is infinite, if this is finite and I is not transient, then I must be recurrent, so this will be infinite. So using contradiction and the above theorem, you can easily conclude this corollary. So now there is some remark, some simple observations. So if state I is transient, okay, then you have seen that if state I is transient, then this series will be convergent. And you know that if a series converges, then using nth term test, we know that its nth term, that means PIIN, that must go to 0 as n goes to infinity. This is the standard result from real analysis, that if summation n from 0 to infinity PIIN is finite and all of them are non-negative numbers, then their nth term must go to 0. So if state I is transient, there is a sufficient condition that PIIN must go to 0. Remember that this is not a necessary condition. Sorry. This is a necessary condition. This is not a sufficient condition. That means you cannot say that if PIIN goes to 0, then state I is transient. You cannot say that. But if state I is transient, PIIN must go to 0. So what happens if PIIN does not converge to 0 as n goes to infinity? So then, since this was a necessary condition and it does not hold, then I will not be transient. So then I is not transient. And if I is not transient, what does that mean? That means I is recurrent, because either I will be transient or recurrent. So remember that you can verify with this also. And second remark, what it says that state I is recurrent if and only if expected number of visits to state I, given that process starts in state I, is infinite. See, this is very important remark. Why this is very important remark? Because it clarifies why we are saying state I is recurrent. So it says that state I is recurrent if expected number of visits to state I when you start in state I, that will be infinity. That means the process again and again visits to state I. That means state I is recurrent. That means it will repeat. So it is straightforward, not very difficult to show that this expected number of visits to state I, given that x naught is equals to I, is nothing but this summation of probabilities. So very simple proof. So let IN denotes an indicator variable, and it says that IN is equals to 1 if xn is I and 0 otherwise. Okay. So now you can see that when it will be 1, when at nth step the process in state I. So clearly summation n from 0 to infinity in, what it will be? It will be nothing but number of visits to state I. Why? Because whenever process is visiting state I, these INs will be 1, otherwise they will be 0. So if you sum all of them, you will get number of visits to state I. So now we want to find the expected number. So therefore expected number of visits to state I given that process starts in state I. So by definition this will be expected value of summation n ranges from 0 to infinity given that x naught is equals to I. But by we know that expected value of summation in is nothing but summation expected value of in given that x naught is equals to I. And what is this? What you are saying? Expected value of in takes value 1. So it takes value 1 when xn is I, and this given that x naught is I. Otherwise it takes value 0. So this expectation comes out to be, what is this? This is Pii in n steps. So what you are getting? You are getting that this expected number of visits to state I given that x naught is I is nothing but this sum of these transition probabilities. And we have already seen that if this sum diverges, then your state I is said to be recurrent. That means if expected number of visits to state I when x naught is I is infinite, that means the process will visit infinitely many times on an average to the state I when it leaves state I. So this is a very important remark because it clarifies why we are saying the state I is recurrent. So now we will see very important corollary which says that corollary. So we have seen that periodicity is a class property. Now what this corollary says, this says that recurrence and transience are class properties. So it says that recurrence and transience are class properties like periodicity. So in language what it says that assume that I and j communicates to each other. So class property means, what is a class? Class in which those states are there which communicates to each other, and if one of the state is recurrent, then all other states will be recurrent. So that is the meaning of class property. So it says that if I and j communicates, then state I is recurrent implies state j is recurrent. State j is recurrent. It is actually if and only if. So state I is recurrent if and only if state j is recurrent. So or otherwise I is transient if and only if state j is transient. So it says that if I and j communicates, they will have same status. Either both will be recurrent or both will be transient. So we will see the proof of this corollary. So suppose, so see, if we show that state I is recurrent implies state j is recurrent, then otherwise will be other way will be same, because I and j are two states. You can replace I by j and j by I. So suppose that I and j communicates, okay, and state I is recurrent, okay. So we will show that state j is also recurrent. So since I and j communicates, then there exist n and m greater than 1 integers, such that because I can be accessed from j and j can be accessed from I, so there will be some positive probability of going from I to j and going from j to I. So these two, there should be two positive probabilities because these are communicating to each other. So now for some non-negative integer k, we write p I j m plus k plus n. Okay. So what it says, m plus k plus n, what it says that you start from I, not ij, this is p j j. Okay. So you start from j and ended at j. So in between, if I consider that it is at L1 state and L2 state, and the time taken from j to L1 is m, and then from L1 to L2 this is k, and then L2 to j this is n. Okay. So by Chapman-Kolmogorov equations, we can write down that these two states, L1 may be anything from state space, L2 may be anything from state space, and you will move from j to L1 in m steps, then from L1 to L2 in k steps, then from L2 to j in n steps. Okay, this is directly by Chapman-Kolmogorov equations. So now we have many times used that if these are the summations and you choose the particular one, then this summation will be greater than or equal to that particular one. So we are choosing L1 is equals to L2 is equals to j, not L1 L2 is equals to I. So this will be greater than or equal to p j I m p I k p I j n. Okay. So all these probabilities are there. P j I m, this is positive. P I j n, that is positive. So all of them are there. So we just take the sum on both the sides, because this is true for all k, whatever k is inside in between. So k can be from 0 to infinity. P j j m plus k plus n is greater than or equal to k from 0 to infinity p j I m p I k and p I j n. So this can be written as k from 0 to infinity p j j m plus n plus k greater than or equal to, see there is no k here, p j I m, there is no k. So and p I j n, there is no k. So you can take outside these two things, k from 0 to infinity p I k. Now what was our assumption? Our assumption was that state I is recurrent. So if state I is recurrent, then we know that this will be infinity. Why? Since I is recurrent. So by previous theorem, if I is recurrent, then this series will diverge. And if this series diverges and these two probabilities are positive, strictly positive, and this quantity is bigger than this, so this quantity will also diverge. So that means this implies that sum k from 0 to infinity pjj m plus n plus k also diverges. Because this diverges, these two are positive quantities and this is bigger than that, so this also diverges. So now using this divergence, we will show that j is also recurrent. How? If j is recurrent, then we will focus upon pjj r, summation r from 0 to infinity. If we want to show that j is recurrent, and if we show that this diverges, then by previous theorem j will be recurrent. So our aim is to show that this series diverges. And what this series is? This series is nothing but pjj0 plus pjj1 plus dot 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 pjj m plus n plus pjj m plus n plus 1 plus dot dot dot. So clearly all these probabilities are non-negative, so you can write down, if you remove all these, so you can write down this is greater than or equal to pjj m plus n plus pjj m plus n plus 1 plus so on. And what is this? This is nothing but summation pjj m plus n plus k, where k varies from 0 to infinity. And we have already shown that this series diverges. So summation r from 0 to infinity pjj r diverges, which clearly implies state j is recurrent. So we have shown that when state I is recurrent and I and j communicates, then state j is recurrent. So if you replace I by j and j by I, you will get the other way around result also. Now if you want to show that state I is transient, then state j is transient. So that is also easy. You can show that by contradiction. Okay. So now suppose that I and j communicates and I is transient. So we want to show that our claim is j is transient. Okay. So proof is very straightforward using contradiction. So suppose if possible j is not transient, that is j is recurrent. So by first part of this theorem, which we have just proved, j is recurrent implies I is recurrent, which is a contradiction, because you have assumed that I is transient. So it is a contradiction. Hence our assumption that j is recurrent is wrong. So hence j must be transient. because when you assume that j is recurrent, then I must be recurrent, but I is not recurrent, so j must be transient, because there are only two possibilities: either j will be transient or it will be recurrent. So I will stop here, uh, and in next lecture we will see some more corollaries of these results. So what we have done today, today we have basically shown that the main result is that if summation PIIN n ranges from 0 to infinity, if this series diverges, then I is recurrent, otherwise I is transient. And based on this theorem, we have shown that recurrence and transience are class properties. So I stop here. Thank you once again.